Evolution of color difference equations is the topic today. And we'll start off with the fact that color spaces are not uniform or balanced. You can see the image on the left is a rendition of C-Lab color space, and you can see how non-uniform it is with the clustering of kind of the pinks very close to one another. Then you go up and you look at the reds and yellows, and then the green gets really spread out, and you come back down to the bottom where the blues are starting to condense back together. On the right, we have an image of the Munsell color space. It also is not uniform or not balanced, but within the Munsell color order system, each of those kind of chips are equally visually spaced from one another. So if you can see my cursor, these chips are all equally spaced visually apart from one another, as are these over here in the yellows and the reds. And you can see there's a lot more chroma in the yellow than in the blue area. So it's just another example of how things are kind of not balanced with colored spaces, and that's going to present a little bit of a challenge. Start off with the C-Lab color system, or LAB coordinates as they're fondly referred to. And this is a pretty simple Cartesian coordinate system. You start with L and you come up to the lightness level of 58.12, and then you go out in the A direction, in this case 36.41 units, and then up from the B axis in 24.26 units, and that's where this orange lives in color space. Pretty simple, and this is a very common color coordinate system used in a lot of different industries today. And quite simply, we talk about delta LAB, or color differences, and that's simply taking the sample minus the standard for each one of those coordinates. So you take the L differences, the A differences, and the B differences, and then you end up with a total delta E, which is really the straight line distance between two samples. So you can see this is the A, the B, and the L deltas, but the delta E is really the straight line distance between the two samples in three-dimensional color space. We also can navigate that same C-Lab color space using a polar coordinate system. So very simply, it's the same value for L. So we still come up to that 58.12 L value. And then instead of going out in A and B, we talk in terms of hue and chroma. So chroma is the distance from the center or the neutral part of that L scale out to a point in color space. So in this case, the C value would be 44.32. And the hue angle is simply starts at the positive A axis and goes counterclockwise in to 360 degrees. So in this case, we're just before the kind of the 45 mark on in between yellow and red. So it's going to be a hue angle of 38. When we talk about color differences using that LCH color system, we just want to point out that the delta H is not the difference in hue angles. It's the actual distance of this vector here, and what is that is comparing is if that sample and standard had the same chroma, what would be the hue difference? So that's how we calculate that particular metric. We talk a lot about chromatic and non-chromatic colors in color tolerancing, and that's really because the neutral colors, the non-chromatic colors, have that chroma vector less than 10, and that's an area of color space that we're really sensitive to color change. So we tend to use different types of tolerancing systems on neutral colors, and more chromatic colors, or any color greater with a chroma value greater than 10, we tend to use LCH notation and talk in terms of chroma and hue differences there. Again, for less than 10, we're typically using delta LAB notations. So what we're showing here is with those achromatic or neutral colors, we have a bunch of samples that are either visually acceptable or rejected from a particular standard. The standard is shown in the center, and this would be a 3-degree or 3-dimensional plot. So if we just used tolerances on A and B, we would have this square, or it would actually be a cube in color space. What the circle or the sphere represents in color space is what we actually typically visually accept. And again, since we're talking about a neutral color, the box tolerance and the circle or the sphere tolerance would be very, very similar. When we start to introduce chromatic colors, those differences get quite a bit larger. So we kept the similar box tolerance and sphere mounted here, and then we expand out to have all of these other visually acceptable samples inside of this ellipsoid. And what we're showing here is if you were to go with a box tolerance or a sphere tolerance, you would still be rejecting from a specification all these visually acceptable samples here and down in here. And so we really want to include all those to maximize production. And again, this is a finished product. If we're talking about raw material tolerances are going to be well within this elliptical tolerance, just because you then apply application factors and things like that to a process, and that includes variability. Some people will use LCH tolerances, so it's referred to typically as a pi tolerance, and it's shown here in 2 dimensions. So you have your standard again in the center. This is your hue angle, so you're changing hue, and this is your chroma vector coming away from the center of color space down in this area here. So one of the things that we like to point out when we're looking at mismatches or things that don't match is where is the color difference coming from? In this particular case, we have a standard and we have a sample 1 and sample 2, and yet both of those have the same delta E value of 1. But you can clearly see that sample 2 is, let's say, a worse color match than sample 1. That's really for 2 reasons. Number 1 is all of these equal components, your delta L, delta A, and delta B, all of those differences are equally spread out across all 3 components. In sample 2, all of it is coming from a single component, and that happens to be the A value. So the A value is red-green, B value is yellow-blue. So what we're picking up here is red-green is a hue difference, and all of that color differences is coming across in terms of a hue difference. What's important to know here is that when we do look at color differences, we first see hue differences, we then see chroma differences, and lastly is what we're sensitive to, and that's lightness darkness differences. There are limitations within the C-Lab system. Like I spoke about early, it's not very uniform. And what we show here are ellipses of all equal to each other. And you can see how the ellipses in the center of color space are very, very small and circular-like, so like a sphere. And as you get more and more chromatic, they tend to get larger and they tend to spread. It's also interesting to notice that the largest tolerances are in the green area, and then down in the blue, yellow, and the red area gets really elongated. So what we know is when we look at reds, we can see a red shift to the blue side or shift to the yellow side very quickly. So we're really sensitive to those color changes. So delta E, the original delta E equation, was done in 1976. And since then, we've had a number of different changes that have come along, and we like to try to take advantage of that whenever possible. All three of these different delta E calculations the goal was to have better agreement with visual color perception. And again, this is of finished goods, not necessarily raw materials. So the first one I'll talk about was published in 1988, and that's the CMC tolerancing system. And that was introduced by the Society of Dyers and Colorists in the UK. This was all done for textile samples, and it was based on elliptical spacing of LCH, not the rectangular spacing. It is recognized around the globe as a standard, that international standard that people follow, and again, heavily used in the textile industry. And what the variables are is it was the first time it allowed to have different weighting systems for your L scale and your C scale. So it was a way to control the ellipsoid and how forgiving you wanted that to be. So we always talk about delta E CMC with an L to C ratio. And typically that L to C ratio for textiles was 2:1. And if you think about textiles, a lot of textiles have a nap or some directionality to them. And that was one of the things that influenced the L value and the variation of L in color measurement within textiles. So 2:1 was very, very popular. Sometimes in the paint area, they would use 1:1, and sometimes in plastics, it would be 1.4:1. Still widely used today, though. CMC is a recognized good tolerancing system, again, for correlating to visual perception. It got a little bit better in 1984 when they introduced delta E 94. And that was, again, based on the LCH color tolerancing system. But it corrected for chroma-dependent colors. And it had really no lightness correction. So we're really correcting for chroma and hue only in the delta E 94. Again, this one, all the sets were done with solid colors only, and it is a recognized color tolerance system for the CIE recommendation in the Technical Report 116. Here, the equation starts to get a little bit more complicated, and now that you have these application factors and you have weighting factors. So your weighting factors are your sub C and sub H for chroma and hue weighting factors, and those are dependent upon the standard. So when you're doing color difference, everything gets calculated from the standard in this case, and your application factors are for lightness, chroma, and hue. So unlike CMC, where we couldn't do all three variables, now we can do all three variables and set accordingly. This is a good example to give you a visual to see how the color differences change or how the calculations are done differently with delta E 94. So what we have on the left is we have just straight delta values. So this plot would be looking at these numbers up here. And you can see the delta E calculation is fairly high. So, we're talking a spot pretty far away for the hue difference, and spots for minus chroma and plus chroma pretty far away from the center where the standard is. When we change that delta E calculation to delta E 94, both those chroma samples fall within the visual ellipse. And now just the hue difference is just outside of the ellipse. So you can come up here and you see that the chroma differences 0.71 and 0.65 are well within the ellipsoid, and the hue difference is 1.18 or just outside that ellipse. And again, usually with these elliptical systems, they're all weighted, and so usually the target would be 1.0. Further improvements came with Delta E C-Lab 2000, and it's very, very similar to Delta E 94, except in the blue area, they noticed that the visual evaluation wasn't aligning up as well. So there was an extended amount of visual comparison that was done for this, and they had a lot more samples in the blue area, and they found that if they could just somehow tilt that ellipsoid a little bit off axis, it would better align with visual evaluation. And here we're showing you kind of an expanded view of color space and those ellipsoids highlighted right here. And this is the area that's really affected in terms of where those color differences are when you go from in C-Lab color space and you talk about these new ellipsoids and being tilted slightly. Again, all advancements to better align with visual perception, because the goal really is to use instrumentation to quality control processes and components, so you end up with a more harmonious end use product, whatever it is that you're manufacturing, whether it be trains, planes, or automobiles. So what happens when we have color difference with color and effect colors or effect pigments, whether you're doing personal communication devices or you're doing washing machines or you're building materials or automotive colors, things change because there's effect pigment in the formula and color begins to travel. In other words, it changes by angle, and that's part of the design. So this is when the measurement world gets a little bit more complicated because you're going to be using a multi-angle measurement device, multi-angle spectrophotometer. And in our case, you're also going to be able to measure sparkle and graininess at multiple angles. So what we see here is one of the most current equations for multi-angle color measurement, where we're starting to introduce measurement geometry. So now this little lambda here is for every angle. You can have different weighting factors. You can have different tolerances, and you can actually have different application parameters for batch tolerancing or raw material work, or production tolerancing, which would be finished product work. And again, you have this achromatic and chromatic equation, and many of these equations will actually can switch based on angle. So you may, for example, might be achromatic at a near specular angle, and then as you get further away from specular, you might become more chromatic. So you might report things in terms of LAB in one part of your report, and that might switch to LCH in another part of the report. Again, these are all weighted tolerancing schemes, and here you see the ability to look at total color difference, and this would be the summation of maybe all 6 angles, resulting in a total color difference, or delta ET is what it's referred to as. So it's total color difference for that one particular color, and it could be that if you have 5 angles turned on or 6 angles turned on, it just will take the average of all of those and report it. The delta effect difference, or delta ST, does the same thing for up to 3 angles of sparkle and graininess. And not to go into a long description of what that is, but it's using camera technology to pick up the sparkle at different angles. So you're trying to see how bright a particular flake would be, or how it's oriented in the paint layer. And then the graininess, sparkle is for direct illumination, and graininess is for diffuse illumination. Or in the automotive industry, what they kind of refer to as how does that look on a sunny day versus how does it look on a cloudy day? And that would be your total effect difference. And then you can, in some cases, people will combine those for total color and effective differences, or delta SE. And that's just, again, taking both of them and the square root of that particular answer. So what are some of the takeaways of the summary for this afternoon? We'll start with color differences have advanced to correlate to visual acceptance, and there's differences for achromatic and chromatic colors. That's kind of been a theme throughout all of the advancements in the color difference equations, and it really started back in 1988 when we really went away from rectangular tolerances to elliptical tolerances. Color tolerances are specific to the type of color being measured. So is it a solid color or is it an effect color? If it has effect pigment in it, we have to take into account extra variables and tolerance for those. Generally, raw material tolerances are tighter than finished product tolerances. So a paint batch, for example, is going to be much tighter and much smaller than that for an automotive plant or appliance manufacturer, office furniture, building materials of all different types. And those different processes all have unique variables to them, and color measurement can be used to help control the processes also, not just be a pass-fail on finished color tolerances. One thing to remember for raw material producers, again, they're really not based on visual tolerances. If you see a visual tolerance not passing in a raw material situation, we really need to look back at the formula and see if you can correct for that. And really, spectral curves become really important here. So you can, a lot of people can read spectral curves and tell you what kind of color differences are just from looking at the curves. Again, colors that include effect pigmentation, the tolerances usually incorporate the color, sparkle, and graininess into the overall tolerance itself. So you can have one number that kind of gives you a nice pass-fail way to look at your process and see if it's in control. Visually validate color differences. Always be looking at things. If you are looking at them and you have people that you've entrusted to visually evaluate product, it's a good idea to have them regularly tested to see if their color acuity is changing over time. If you're looking at things, look at it under multiple lighting conditions. This is a good way to look for metamerism. Metamerism is a phenomenon that things match under one light source and they don't match under another light source. And when the numbers don't match up, whether you're talking to a customer or talking to a supplier, confirm that you're both using the same illuminant and observer conditions. If those change, then your numbers aren't going to be the same. So sometimes they can get reset in a software package or in an instrument, and it's always a good idea just to double check those things. And when all else fails, look at the spectral curves, because it's the fingerprint of the color, and that can really solve a lot of mysteries. So that concludes this short presentation. I guess we can open it up to questions. Sherry, do you have any already?
There's one. So we have some more coming in. Okay, so what is the best way to measure a solid color dark bronze?
Good question. Since it's bronze, it could travel, and therefore a multi-angle color measurement would probably be the best way to analyze that. And if you're using our bitmap, you would also have the sparkle and graininess that would also possibly help you identify what's different in the samples. If you don't have a multi-angle color measurement, you're going to have to use, you probably should use a sphere instrument, because that's going to basically illuminate from all different angles, and it'll give you one number. But depending upon how that bronze travels, if you can't use a multi-angle device, then use a sphere device.
Thank you. We do have another question, and hopefully, Angela, that answered your question. If not, feel free to type into the chat and we can expand on it more. So, could you please explain the calculation of the delta E combination?
I'm assuming that that's for the multi-angle color measurement.
Yes, that is.
So that's taking both the color difference, or delta ET, your total color difference, and the total effect differences. And then you can have this one color and effect difference. If you're talking about DenMod, then that's a very specific way that we treat the multi-angle data, and that is where this equation can adjust to be achromatic for one set of angles and chromatic for another. And just in case it was targeted for delta E calculation, the delta E calculation, again, just a straightforward delta E is the square root sum of the squares. So you take your differences in L, A, and B, you square each of them, and then you take the square root of that. And that's really just what is the straight line vector or distance in three-dimensional color space.
Did that seem to answer your question, or did we go the wrong way with that one?
I can see some of these. So Sam, okay. I'll tackle the CMC one next. Mm-hmm. Which refers to this equation here.
And Sam's question was to better index for measuring paints and plastics.
Right. So CMC originally was done for textiles, but it was also immediately adopted for paints and plastics. And usually the paint industry would not use a 2-to-1 ratio. It would use 1-to-1, and plastics would sometimes be 1.4-to-1, depending upon the texture of the plastic. So if it was considerably textured, then they would use that 1.4-to-1. And again, that's just giving you more variability in your ellipse to have lightness, darkness changes. Since paint is usually always specified at the same or similar gloss level, if you had a glossy green or a matte green, you'd have two different specifications for that. That's why they didn't account for a lot of change in lightness, so they kept it as a 1-to-1, or more like a sphere in many cases. All right.
Craig, it looks like Sam has expanded on his question a little bit. If you can see those, and then we can go back to Anna's question.
Okay, it's bounced around. I have a sphere gloss and a 45-0 meter. Which one is better for evaluating new color matches in paint and plastics? Good question. Real good question. If you see color differences are coming from just texture or gloss, and you want those to be part of your color difference, then 45-0 or 045 instrumentation is preferred. If you see that those texture and gloss differences and you don't want those to be part of a color difference, then you want to use a sphere instrument and look primarily at specular included measurements.
Sam had also asked that they needed some help to evaluate the curve and other software features, and if there was a training class or some online information that could be viewed. I do know that we have some videos on YouTube, but it would probably be best if we could, we'll get your information and get you in touch with our regional sales manager can come visit and help you.
Sherry? Sherry, can you hear me? I think we lost Sherry.
Oh, can you not hear me?
Maybe I got cut off for a minute.
Okay.
So I guess let's continue down some of these questions. I'm trying to follow them, but
Anna had asked what was the best way to measure color of non-woven fabric materials.
Non-woven fabric materials is probably going to be best measured with a sphere instrument. Most of the time you would use those in a specular included mode, and that's really for even woven non-fabric material like tarps and stuff like that. But most textiles are all done with sphere-based instruments.
What is the difference between CMC from 1988 and CIE from 1976?
So all of these tolerancing systems are all using the C-Lab color space. So the color space does not change. The way that you calculate delta E does change. The delta E calculation for 1976 was in this case, it would be shown here with the sphere. This is a two-dimensional circle, but in 3 dimensions, it would be a sphere. And that's just to say that in this case, if each of these axes were 1, when you're in between the finite axis, that is it's a sphere dimension. And prior to that kind of a delta E calculation, many people used tolerances of L, A, and B, and they would change those cube tolerances depending upon what kind of color they were dealing with. And then in CMC, you go to a elliptical based system that is based on this representation of how these are all these ellipses are the same tolerance, and they self-adjust in color space based on where you are, either as an achromatic or a chromatic color, and they'll automatically produce the same ellipsoid for a given tolerance.
Caitlin, I hope that answered your question. We will be, we can send out the presentation as a PDF, and we are also recording, and you will receive the recorded presentation as well. Which kind of light source is used for measuring flop index in effect pigments, flip, flop index, and directional or diffuse?
So the light source, the instrument has its own built-in light source for illuminating the sample, and then you detect the reflectance at each angle, and then you calculate from each spectral curve your LAB values for each angle. The flop index is really the difference in L of the 15 and the 110 angle normalized by the L value at 45. So it's really just an indice that looks at how does the lightness darkness change with those different angles of detection. It's not considering any illuminant or any visual conditions on how you're viewing something. So technically it's directional, it's not diffuse, because all of your multi-angle color measurement devices are all directional. And that means if you measure it one way and then turn it 90 degrees, if the sample is directional, you'll get different numbers.
Hopefully we covered that enough. If not, feel free to keep adding to the chat. Oh, and April, good question. Are there any recommendations for textured paint?
Textured paint, we actually have a solution that we have. It's called a Spectra 2 profiler, and it measures 45-0 color, and it uses camera technology to actually quantify and define how big and how significant the texture is. If you're just looking at a textured paint product and you want to just use a color measurement device, typically a sphere instrument is going to be preferred because it's going to help to eliminate the texture as being part of the measurement. So you can look at the color difference as something that you might have to change in the formula itself.
In April, we can send you more information on that product then as well. Mark has a question. So is DE2000 the current best formula to use? Are they working on any others like CIE CAM 02 or others?
So I'll answer that in reverse. They're always working on new things. It just becomes harder and harder to make significant advancements to formulas that are correlating to visual evaluation. And a lot of the advancements have been in the area of multi-angle color measurement with effect pigments. But typically, I could take the political out here and say that's could be a personal choice, but we think that using the latest and greatest is always the best way to go. It's where it starts to become more of a discussion is if you have a lot of historical data that you tend to refer to and you don't have a way of maybe going back and necessarily looking at all those things, then maybe it's something that you want to consider. But if again, these are tolerances used to correlate with visual evaluation. So if you're making a finished product, take advantage of the latest and greatest equations. So another question here from Sam, does BIC recommend that a color booth be used as well as a meter to view color samples? Sometimes my LAB values are within spec, but the color looks off. I think it could be metamerism. It could, if it is metamerism and you cycle through the different light sources in your booth, then typically you'll find a light source that all of a sudden things don't look right under, or they look light and let's say light and red on one light source, and then they go dark and blue on another. That could also be something to look for. But yes, if you can use a booth or a luminaire, always use those. to look at your samples visually. And we would also recommend that you look at things before you measure and then take a look at numbers, if possible. Can a BIC perform in technician color perception level, or is there something online that can be taken to see if you can perceive colors correctly? Another good question. There are tools online that allow you to do color perception testing online, but there is a Farnsworth 100 hue test that is that we carry, and it's a popular one for. It has 4 trays of 25 samples each, and you have to put them in order, and it gives you instructions on how to rank those answers.
I think our Guardco brand may sell a couple as well too.
Yep.
We can look into that for you as well too. Make sure that you have information on that.
We got here from when visually inspecting, what type of light and how many lumens should we use to pass fail?
On the production line.
Okay. The type of light, typically people are moved towards a D65 light source, and then the lumens, I'd have to get the specification off of, there's a specification set out by the SAE to use overhead luminaires, and then there's so many lumens, so many inches away, but I don't have that at my fingertips right now. So I apologize for that.
We can follow up with that question.
A follow-up to the light booth question is usually also, when you're looking for metamerism, D65 or D75 is going to be your bluest or whitest light. And then usually incandescent or horizon is the most red or yellow of a light source. So start with those two, and then throw in one of the cool white sources as a third, and that usually helps to pick up on metamerism. Follow up on my question about flop index, chapter 2, industrial color physics book has been mentioned. The flop index is measuring using diffuse light. On the contrary, I agree with you. So I don't know if the original flop index was done differently, but I know that the flop index is used widely in automotive paint, and especially in refinish colors, because it's also another way to take databases of many thousands and reduce them down to a couple of hundred colors that they can search quickly with. So it's a real good way to eliminate things that don't travel as much as a given sample if you're looking to do a lookup or something like that. Continue with non-woven fabric material. If I wanted to make a comparison evaluation between different materials, is it accurate to use color reader LAB and use as a white black sheet of background to make comparisons? Results in terms of delta E. Basically, what I want to measure is opacity to evaluate how transparent material is. Take the results of 2 different backgrounds and use the delta E. My assumption is that it's less. Delta E means the material is opaque. Okay, so basically what you're describing is taking and measuring a sample over white and over black, and there is actually an opacity indice, which is exactly doing just what you're describing. It's comparing the deltas between 2 samples, and the more opaque a sample is, that you'll have smaller and smaller differences between those 2. Sorry for all the questions. Is there an LED light source in the BIC meters? Seems like more stores are going to this, but we do not have a current meter nor in our booths. That's a really good question. So the light sources in many BIC instruments are LEDs. So we have a long history of how to manage LEDs and how to get consistent output, especially over wide temperature ranges. But that's the illumination part of an instrumentation or a spectrophotometer. I think what you're referring to is there an LED illuminant that is used in calculating color differences. So when you calculate color differences of LAB, you are taking into account some type of light source or lighting environment, and that's represented by the illuminant data. Illuminant is just a lookup table that all of the spectrophotometer manufacturers use, and so that we all use the same D65 illuminant, we all use the same cool white fluorescent one, and to date, they have not standardized on one LED output. In some software packages, you can enter your own illuminant data. Some people have been, inclined to measure their own viewing environment, and they feed that in to see if that changes anything. I would say stay tuned because the LED market is changing all the time right now, and many of the manufacturers of LEDs are trying to achieve D65. So that's the goal, at least. We use D65 and cool white fluorescent, but I think the cool white fluorescent isn't used anymore. So for those of you out there with light booths and cool white fluorescent bulbs, if you end up replacing the bulbs on your own, make sure you use the same manufacturer every single time. The different manufacturers use different phosphors to coat the inside of the tubes. And if you are changing in between manufacturers, that's going to be a variable that could throw off some color matches. Always best to go with the manufacturer's recommendation. How often do we recommend testing color perception? I can tell you over the years, I've seen it used as a screening tool for new hires, especially if they're going to be doing a lot of color matching work. But typically after somebody's been tested, they go to either a yearly or every other year testing, just to continue to get that data point. We've got SAEJ 1767 got revised recently to correct for typo on delta E equation. I am wondering if you can provide any more info on that. How was it corrected editorially? Got me stumped on that one. I don't know what the editorial correction was.
I'd have to. Wasn't on vacation this week. Maybe she would know.
I mean, if it was an editorial typo, then I don't know if they did something other than that.
We can certainly take it to check on that one.
Yeah, we can ask Sandra in Germany. I think she keeps track of all the changes. Mm-hmm. To capture sparkle, how much lux is necessary for the light source? So the good news is within the instrument, the light source is fairly bright and the measurement time is fairly short. So, and we take care of calibrating all that out for the camera and the light source technology in the instrument. So you'll always have enough light source or lux in the instrument to capture it. If you're looking at trying to simulate that, a pretty bright flashlight or even a floodlight would be something that would be used. And a lot of the paint manufacturers have set up on the wall where they have a floodlight and they can walk over and turn that on, and they can look at two different samples if they're doing color matching to try and see if they've got the same sparkle in two different samples. And there's also some handheld devices, light sources that are used commonly in the refinish industry, and they use them to do two things: look at a color match and emphasize that amount of energy on the sample to look at the flake, and they also use it in a larger area to look at how the repair has been applied, and is it fully covering the new bumper or whatever they put on. We would agree that cool white fluorescent is not being used that much anymore. When the retailers changed over to fluorescent sources over 30 years ago, 40 years ago, there was a big push to change over because things were metameric in the stores. But that is not the case that much anymore. Is there any standard criteria help us to tell apart directional light source from diffuse ones? I'm not sure I understand that totally, but if the light source is diffuse, that means you're getting lighting from all different directions. So a light booth has that diffuser in it, and that's to help the light go through the diffuser, hit the walls of the light booth, and then land on the sample as you're viewing it. As opposed to having a floodlight or something that is like a spotlight or a flashlight that would be directional. In the instruments, most 450 or 045 spectrophotometers would be considered directional, and you can see that because there's no sphere in the instrument. All sphere-based instruments have some diffuse light, and in our multi-angle instrument, if you look inside of that, you'll see two hemispheres, and that is for that diffuse illumination. Oh, so thank you for the clarification on SAE J1767 had a negative sign instead of adding the three values. So which illuminant should we be used for lawn care products? We use D65 and cool white fluorescent. Screen's moving fast. So that's it's good that you're using D65 because that's where most of these products are going to be seen and used. Cool white fluorescence, because a lot of the retailers that sell lawn equipment might have cool white fluorescent in their showrooms. So those would be good if you're looking to try to catch any type of metamerism. Then I would look at either horizon light or incandescent, because that'll be the extreme case for you. So again, those illuminants can be selected on an instrument or in the software package, depending upon who's you're using. You can actually, a lot of them will allow you to have a primary, a secondary, and a tertiary, so three different light sources or illuminants that you can have your delta LAB values calculated under. And then in your light booth, try to use those exact same light sources in the light booth. Okay. It's the illuminant code in the meter. So the illuminant code in the meter or in software is just going to be, a lot of people call it the light source or the viewing condition. But it's really, if it's coming out of software, you're looking at illuminant data to make your LAB calculations. Regarding, may want to review CIE guidance on measurement of color, CIE 015-20-218, colorimetry, 4th edition. I've got homework to do, I guess. So it did standardize, publish new. So this gentleman's saying that they did standardize and publish 9 new LED illuminants in 2018 document. Preferred, and that the CIE Delta E2000 is the preferred color difference equation to use for industrial color evaluation. We would agree with that also. We'll have to look at that, and if we can get our hands on it, maybe that's something we can ask our software people to add to our software package so that we can calculate that. Thank you for that suggestion. Sherry, did we catch all of them?
I believe so. I think Sam needs maybe some more assistance, which we can reach out to him about what Horizon is and how that is used.
Okay.
There's one more that we may have time for. Which kind of standard illuminant has been used in the BICMAC, D65 or D50?
D65 is the standard illuminant that the effect measurement industry really defaults to. D50 has been used in the printing industry, and there's not a lot of multi-angle color measurement going on in the printing industry. So D65 definitely is the go-to viewing condition, and therefore the standard illuminant in the BICMAC.
I think we were able to get through all of them. As I said, we do capture all of the questions, so we can certainly reach back out and get in touch with you to make sure that we covered everything. If anybody has any further questions, you certainly can always reply to any of our marketing emails that we send out. You're also welcome to sign up for as many of the webinars when you get one of the invitations, because the ones that we send from Bic Gardner USA, they're all kind of listed there, and you can sign up for as many as you want at a time. And we thank you so much for attending today.
And we can also follow up, Sherry, on a one-on-one with any of the companies and use specific samples that they're using or measuring, and do that. Something during COVID we become very used to doing. So thank you very much, everyone, for your attention today.
And we hope to talk to you again soon. Thank you.